this video, we'll talk about logarithmic functional forms. And so far we know that the coefficients in a log-log model have percentage change interpretations. Or in other words, we can literally ignore the units of measurements for any variable that appears in log form. So this could be, let's say, if we change the units from dollars to thousands of dollars, or from thousands of dollars to dollars, that would not have any effect on a variable's coefficient when that variable appears in log form. Okay. So later on we will look into quadratic and interaction terms as well, and how those are introduced into the regression. But all of these different types of nonlinearities or nonlinear relationships that we are trying to establish help us in improving the interpretation and improving the fit of our regression models. So we'll start with an example here in which we are trying to predict the price of homes based on some measure of pollution, which is the level of nitrous oxide in the area, and the number of rooms in the house. Okay, so this is rooms is really the median number of rooms in the house in an area. Okay, so notice here that you have a log model, at least when it comes to measuring the effect of pollution on housing prices. So here, when we think about beta 1 is essentially an approximation, and it tells us the elasticity of housing price or home prices with respect to pollution. However, when we think about beta 2, notice y is measured in logs, but this x is not. So when we are interpreting beta 2, we are saying that this is the approximate percentage change in home prices when rooms increases by 1. Okay, so this is something you want to keep in mind. However, one of the things to think about is that approximations using logs may not always be good, especially when there are larger changes that we are considering. So you can think about, for instance, the fact that, when we're thinking about approximations, we really are saying that log of x1 minus log of x naught, this type of an expression, basically, I shouldn't put equal to, this approximates what is the proportionate increase in x. Okay, so this is just the interpretation of that would be measured in this way. Okay, now we can take an example and see that this left hand side might be an approximation, and this right hand side is actually measuring the accurate response. So let's think about if x1 was 4.2 and x naught was 4, right? If you calculate what the left hand side is, let's say the left hand side equals log of 4.2 minus log of 4, right? This is equal to 4.88%, okay? But if you calculate more generally what the percentage increase is in x going from 4 to 4.2, then you can calculate it as just being 5%, okay? So notice this is a more accurate measurement. I should take a different color here. This is a more accurate measurement. However, 4.88% is the log approximation is close to 5%, but it's not the exact estimate. Okay, of that. So this is what you want to keep in mind, that logs are only approximations, and as these increases become bigger, those approximations may not hold. Okay, so logs are used a lot, like we just saw in the home prices example, but a more precise calculation of the percentage change in y based on a change in x is given by this formula right here. Okay, and we'll take a look at how this formula is to be used. So this formula can be further simplified if we were interested in just looking at what is the effect of changing median rooms by 1. So if the number of rooms, median rooms, were to go up by 1, what would be the effect on home prices? We can actually calculate exact change or exact percentage change in home prices, y, by using this formula, right? So here we are, notice here we had change in x2 and we've just plugged that equal to 1. Okay, so this is why we have this expression. So remember that if beta 2 hat is not too large, this will be closer to the simpler estimate of 100 times beta 2 hat. Okay, but sometimes this can be different. Now let's try to illustrate this point by using some examples here. So let's say that the effect of increasing median rooms by 1 is 30.6%. Okay, let's say we estimated that model that we described before, where you have log of prices, and this is regressed on log of nitrous oxide plus, right? So you have the intercept, so I'm not writing that, but you're basically regressing that on nitrous oxide, log of nitrous oxide plus the median number of rooms. Okay, so this is your regression, and let's say that the beta 2 hat, which is the coefficient on rooms, comes out to be 0.306. Remember that that is a log approximation of the effect of adding one more room on the price, on the home price. However, the exact percentage change for increasing the number of median rooms by 1 is going to be 35.8%. So if you apply that formula, 100 times the exponent of the beta hat that you got, which is 0.306 minus 1, you would get this number. Okay, so this is really the exact change. Okay, so that's very different than 30.6, and notice this is not going to be symmetric. So if we wanted to understand what is the exact percentage change for decreasing the number of rooms by 1, that is going to be 26%. So again, you can plug this into the formula, but this time, instead of taking the exponent of 0.306, you're looking at the exponent of negative 0.306, and that comes out to be negative 26.3%. Okay, so this is basically saying that if you decrease the median number of rooms by 1, then there would be a 26.3% drop in home prices. Okay, and this is all coming from the nonlinearity of the exponential or logs or these functions. So remember that when we use the log approximation, this number right here that we said was beta 2 hat was 0.306, this is going to lie between on the I guess on the upper limit, it's going to be 0.357, right, which was this number right here, and the lower limit of this would be 0.26. Okay, so in absolute values, if you think about the absolute values of the numbers that we just came up with, negative 26.3% or 35.8%, the approximation is going to lie somewhere between the absolute values of those numbers that we computed. Okay, this is something to remember. Now we have very many reasons why we might be interested in using logs or natural logs. Other than the fact that we have percentage change interpretations, we have this effect that we can ignore that, or we have this implication that we can be ignorant of the units of measurement of those variables, okay, when we use logs. So you want to remember that. Now, logs would only make sense when variables are strictly positive, okay? And we'll talk about some other advantages in a little bit. But what logs also do is that logs reduce the variation in a variable. So let's say you had a variable y and there were like maybe 2 outliers. And let's say y was salary data. Okay, so maybe this is salary data for a lot of individuals, and there are 2 outliers. Maybe there are 2 CEOs thrown in our sample. But when we take log of y, that variability, that variance in y gets greatly reduced. Okay, so you can always take a look at summary stats, for instance, for y and log y and see if this is true. Okay, so remember that if we take logs, the advantage is that the OLS estimates are less prone to outlier influence. Now, there are certain limitations of logs that if y is greater than or equal to 0, but y is equal to 0 is possible, we usually cannot use log of y, right? So log of 0 is not defined. Okay, so sometimes there is this trick that we do where we basically use log of 1 plus y. So if let's say your y is taking values 0 or close to 0, right, y looks like this. So we can construct another variable, 1 plus y, where we just, right, we just use this variable as our dependent variable, okay? So that's something that can be done sometimes. Also, it's harder to predict y when we've estimated a model for log y. So that's something to remember, but sometimes we just want to compute elasticity, so logs are fine. Okay, and one other thing to remember, even though I've mentioned, what logs do to the variability of a variable, when y are fractions, okay, or proportions, and if y is taking a value very close to 0 for many, many observations, then the log of y can have more variability than y itself. So there can be some issues in predicting that variable. So when do we use logs? So simple rules here about using logs. Logs are typically used for dollar amounts that are always positive, okay? As well as for some variables such as population, okay? Where there is a lot of variation, right? So you know that population is strictly positive, and dollar amounts, like salary data, if you're working with salary or wage data, you're going to have strictly positive values. Logs are perfectly fine to use. However, logs are used less often for variables measured in years, for example, such as schooling or age and experience. So remember that we often want to know what the effect of increasing schooling is by 1 year and not by a certain percentage. We usually don't say, if I gave you 5% more schooling, what would happen to salaries, right? We're basically saying if schooling were to go up by 1 year or experience was to go up by 1 year, then what would happen to salaries? So remember that you cannot use logs when we are talking about something that's measured in years. Also, logs are used less frequently for variables that are already in percents or proportion. So think about a variable like unemployment, for instance, right? So unemployment rates could be 6%, 5%. They're always measured in percentages, right? So a change in unemployment, let's say the unemployment was 5% this year and 6% the next year. This is giving you a 1 percentage point change, right? So the units of variables that are measured in percentages are percentage points. So in which case we would not take logs of these variables because the interpretation will become difficult. Okay, so you want to keep, if something like unemployment rate is what you're working with, you want to keep unemployment rate as it is and not take the logs of unemployment rate. Okay, and notice here, when we say unemployment is going from 8 to 9, if it's already measured in percentages, that's a 1 percentage point increase. But really, if you do something like this, 9 minus 8 over 8, you would see that this is approximately a 12.5% increase. Okay, so, and if you take logs, that's like a 0.118, which is a 11.8% increase, which is again an approximation to this. So try to use percentage points and avoid logs for variables that are measured as fractions or proportions.